The binomial theorem of the zeta function and eta function is established in all positive and negative domain, and the binomial theorem of the zeta function and eta function for natural numbers is not established because the gamma function of the binomial coefficient becomes a negative integer, which is the pole of the gamma function, that is, infinity. The binomial theorem of the eta function is established for negative integers, but the binomial theorem of the zeta function for negative integers requires a correction term due to the pole of the zeta function at s equals 1. Rather, these properties of the zeta function and eta function make the interpretation of the zeta function and eta function difficult and obscure. Mathematically, the binomial theorem of the zeta function and eta function should naturally be established, and I think it is not a problem that requires proof. In the already published Riemann hypothesis, the gamma function relation of the zeta function and the eta function is derived based on the binomial theorem of the zeta function and the eta function, and the integral of the zeta function and the eta function in the negative domain can be defined. If the gamma function relation of the zeta function and the eta function is inversed, it is the same as inversion of the binomial theorem of the zeta function and eta function. If the subordinate zeta function 4, 1 and 4, 3 are added, it is the same as the odd zeta function, and if the subordinate zeta function 4, 1 is subtracted from 4, 3, it is the same as the odd eta function. The red odd zeta function is the zeta function of 1 minus 2 to the minus s power, and the sum of the subordinate zeta functions 4, 1 and 4, 3 in blue and green shows an error of more than 10 decimal places. Therefore, the error between the blue and green odd zeta functions is also more than 10 decimal places. Also, the difference between the subordinate zeta functions 4, 1 and 4, 3 in brown and purple is more than 10 decimal places. At s equals minus 2, the odd zeta function is a trivial zero and the odd eta function is minus 1/2. At s equals minus 1, the odd zeta function is 1/12 and the odd eta function is a trivial zero. At s equals 1, the odd eta function approaches pi over 4 equals 0.785898. GeoGebra shows the binomial theorem of the zeta function up to s equals 1.62. But the binomial theorem of the zeta and eta functions holds true in all regions.